Welcome back to the Cycle World Podcast. I'm Mark Hoyer, the editor-in-chief. I'm with Kevin Cameron, our technical editor. This week's topic is the Honda NSR500, starting with the NS500 triple in 1981 and everything that evolved from that. Honda finally made the decision not to try to do really neat, technically complex four-strokes and embraced the pipe organ.
Yes.
I think the ultimate expression of the NSR 500 was really Mick Doohan's between 94 and 98 when he won 5 championships, which everyone decried as boring. And I guess in some senses that's right. It was, boring in the sense of it wasn't the hammer and tong battle and the brave soldiers clawing it out to the death. But when you get somebody who's technically dominant like that, it is a beautiful thing. 97 was his best season, 12 out of 15 races, dominant in 97. How do we get there, Kevin?
Well, I think Honda had, of course, some experience in motocross by that time. By that time, I mean 1981, because that was well accepted as a two-stroke area. And it was not an easy development because Honda started out swinging 2 bats with the 500, which had the fuel tank hung under the engine and the exhaust pipes routed over the top of the engine. The theory being that when the English talked about a low center of gravity being the heart of good handling, nobody had really questioned it. And Honda went ahead and built this thing, and it was slow in roll. It didn't change direction very quickly. And that was a handicap, which prevented them from winning the championship in 1984, which was the year of introduction. And instead of following the clear trend toward twin aluminum beam chassis, this bike had a kind of, a collection of an Omega-looking element and a lot of aluminum tubes going this way and that with carefully worked out junctions. And when they got it into combat, it didn't turn well. It pushed the front. Freddie wanted the engine moved back. It was eventually moved back. I think by South Africa time, they were thinking about it. And it improved it. But basically, what Honda was doing in this period was catching up from zero to where two-strokes were. And the previous bike, the NS3 or NS2, whatever they called it, was a triple, and it had been designed according to Shinichi Miyakoshi's idea of let's build a 250 with the 100 horsepower. And he had gone to the Dutch TT, and he had seen that the twins on that course were remarkably fast. Not as fast as the 500s, but putting 100 horsepower into something as light as a 250 looked like a good combination. And that's what they built for 1982.
But Austin would be a good track for that type of strategy. Not every track would be a good track for that type of strategy.
True. But the crazy thing is that 3-cylinder bike won at Spa in Belgium, which is a wide open throttle kind of place. And part of that equation was that the 3-cylinder being fairly light and having less power overall, started the season with 108 horsepower. It didn't tear up its tires the way the Suzukis and the Yamahas were doing. So at the end of a race, Freddie would would have the others at his mercy quite often, because that little bike didn't have the torque to go through corners in a continuous slide controlled by throttle. And I think at Silverstone, Freddie had to do most of his turning just as the tachometer rose through the torque peak at a couple of places in a long sweeper. So his line ended up looking like what the English used to call a threepenny bit, which is a coin that is a polygon and not a circular disc.
Helps to be Freddie Spencer in that situation, doesn't it?
Oh, yes.
Got it.
And of course, Freddie, well, when I first had the opportunity to talk to Mark Marquez, he said his first year was every lap like qualifying, he said. And so I think that Freddie was doing something quite similar. He was pushing himself to his maximum. And his maximum was appreciable. So in '83, the power of the triple rose finally to 128 horsepower. The power band was always the same. The engine came in at 98 and it signed off at 11. So that gave him 1,200 RPM to work with, pretty much like an old-time Manx Norton. And that's a good reason to have a 6-speed gearbox. Freddie would be given a new engine, and he would put 300 kilometers on it, and the main bearing saddles, these were magnesium crankcases, would be sort of oval. And those cases would be sent back to Japan, be remachined and rebored for one more 300-kilometer go. Because he would hold on when he couldn't get at the shift pedal because the bike was leaned over. He just let it rev. What else could he do? And it pounded the cases pretty well. And of course, magnesium is not the most stiff metal you can find. It's sort of like super cool butter, but it's light.
Electrified dirt, it's often called.
Dirt. Yes. Was that Harold Willis at Velocet that used that term?
I think so, yeah.
Yeah.
What about ATAC? Automatic torque amplification chamber.
One of the things that you have to bear in mind about this era is that in some cases, the manufacturers were willing to copy. For example, when the Big Bang firing order came along, everybody had Big Bang as soon as they could put another crankshaft in it that had the crank pins moved.
We'll have to spend some time talking about that.
Yes.
But go ahead.
But in other cases, there was that Honda way or that Yamaha way. And Yamaha's way was 2 counter-rotating crankshafts. Honda way was 1 crankshaft. And each company on the quiet built what they took to be what the opposition was running, just to check that there wasn't something they overlooked. And this is very common. Manufacturers do this kind of thing all the time. But in the case of the 3-cylinder, evolution of the engine in terms of reliability was continuous. They were constantly getting new pistons. There was all kinds of concern about connecting rod, big end bearing life. And they were, in Jody Nicholas's words from long ago, holding it together with their knees. And this is what happens in racing. It isn't something that can be determined in advance by using mighty supercomputers. There's no experience, no substitute for experience. So you get to the track. They're the engineers. They have puzzled looks on their faces. There's Freddie with his engineer Irv Kanemoto, and they're doing whatever they can. So Freddie was champion in 1983, and everyone else had four-cylinder bikes, and they had been blindsided by this tire-kindly, low-powered bike with a mad genius as rider. Freddie, the wonderful thing about Freddie is that he always had that choir boy innocence in his face. He looked like he's glad to see you, but it could be that he just came through the ceiling in another room. It's like everything's so strange. It's all different here. And the kind of thing that he could do was to wake up in the morning and tell his engineer, Irv, I don't think we ought to be here. And because when you first wake up in the morning, are you ready to slide down the fire pole and set off for the biggest conflagration in the city's history?
Well, I'll tell you what, traveling in this job and being in different time zones and testing bikes, just showing up at Catalunya to ride a Suzuki Hayabusa at the original press launch. You wake up in the morning and you're in a different time zone. You're really tired and you're like, "What? I don't feel that happy right now." And I mean, I don't know what it's like to show up for a world championship, but when you got to show up and do the job, sometimes you got to really overcome that morning feeling, especially in a different time zone.
So they would start talking about gear ratios or about tire choice, and little by little, everything would normalize. And then Freddie would go out and do magnificent, brilliant things. And this was not the result of some high-level analysis, because when people would say, well, what about turn 7? He would put his hands up to the imaginary handlebars and get that puzzled look. And you could tell that he forgot to check, because he was doing it as things came at him, he handled it. And usually with tremendous brilliance. And of course, I like to say that the top rider in a given era is the one who best implements the value of the technological solutions that are new. And we know that Kenny, for example, knew that motorcycles turn badly but accelerate wonderfully. So his corner strategy was to get the turning that the motorcycle doesn't do all that well, get it done quickly at an early apex, get it turned, and shoot it out of there. Acceleration, emphasis on acceleration. And Freddie, you can't tell if he said to himself, well, if I go into the corner a little faster and the front end starts to wash out, what if I go in faster yet? And, well, naturally, the answer is you'll fall down. Your helmet will fill up with gravel as you slide to a stop. But he had worked this out on a couple of dirt tracks in Kentucky as a younger man, as a lad, actually. And what he'd found was that if you went in faster than the speed that would wash out the front, and then you gave a little whiff of throttle, the overloaded front tire would be pulled back up the curve, the load versus grip curve, to the peak, and you'd go around the corner. And if you listened for this, you could hear it.
There's
And
a great photo of Freddie at Suzuka with a black line coming off of his front tire with the bike. I believe it's Suzuka, black line coming off the front tire, and he could just kind of do that over and over. It seemed like.
yeah, and of course, this was a tremendous asset, but again, you had to trust this because it wasn't going to be a cooperative analytical effort as it is with some riders, because Freddie was going to solve the problems as they came. And of course, in '84, when they started with the NSR500, the one with the fuel hanging underneath the engine, Michelin were making slick tires. And so Freddie's bike was a test vehicle for the slick tire revolution. And this, the radial ply revolution, pardon me. And so this was an additional complication because he was brilliantly able to sense what the motorcycle was going to do next. And this is something that every rider requires, because if you randomize the motorcycle, you're going to slow down until you feel like it's not going to hurt you. And that's what most riders do. We're sensible people who know that we're not Freddie. And so we don't want to have to cope with things that are new to us. So we ride sanely and sensibly. And Freddie had found that he could cope with these things, and he rode as if he expected to. So the three-cylinder wasn't going anywhere with respect to power, because it was about developed out at the end of '83. And there had been discussion about what would be done for '84. Would they build an updated three-cylinder? Would they take advantage of the rules which allowed four cylinders? How would it go? And they decided to do this major pioneering in the form of putting the gas underneath and the pipes over the top. And that was a mistake, but mistakes teach you so much. And shortly after that mistake, all the manufacturers seemed to have bought rigs for testing the polar moments of various things, whole motorcycles, just the wheels. I remember seeing those apparatus at Eric's place, Eric Buell. Of course, he was terribly interested in those variables. Anyway, they finally decided that they would build a four-cylinder, and as soon as the updates for the three-cylinder that were intended for '84 were finished, they built a single-cylinder test engine, 54 by 54.5 millimeters, and started testing. And when '84 season began, the motorcycle wasn't terribly powerful. In the early testing, they had found that the three-cylinder had higher top speed, but the four-cylinder accelerated better. And there was a lot of intensive cylinder development going on. And that's probably why the exhaust pipes tended to stay the same, is because they had a lot of catching up to do. And those cylinders had a center divider exhaust port that was T-shaped, wide at the top, narrow at the bottom. The idea being to have a lot of area through which the cylinder pressure could leave the cylinder very quickly, so that then they could get on to opening the transfers and starting to refill the cylinder. And Yamaha eventually switched to this T port, but it wasn't without trouble. And lots of people out there have had the experience of having the exhaust port divider leave a black streak on the piston. Well, what if I drill little holes in the piston? Some mixture will come out through those holes and lubricate that divider. Well, it helped a little bit. How about if we take a rubber wheel and kind of relieve the divider a little bit to lower it? Well, that helped more. And when the piston closes, that huge wide exhaust port, it gets a bit of a slam, and the piston is hot, so the material is softened. And so what would happen is that the top edge of the upper ring gland would be forged down over the ring and trap it in its groove so it stopped sealing. So that meant before you could fit new pistons, you had to take your trusty triangular file and bevel the edges, particularly the top edge of the single piston ring groove, so there was no material to be forged onto the piston ring. And all this preparation was handwork. It didn't come in the little box from the manufacturer. So it had that old-timey quality, the same as back in the two-stroke days. On any night at the paddock, you could hear the whine of die grinders as people were doing final detailing on a fresh set of cylinders before putting them on their engine. So 84 was a learning year, and Freddie was not champion. That was Lawson's year. And this was because of all the stuff that Honda had to collect information about, digest, and decide how they would treat it. And what this all amounts to, I'm not going to bore you with a lengthy, and then they did this, and then they did that.
I just got to point out, Kevin does notes for these podcasts. We talk about it, and then he runs off and does his thing. And he's got, he's got a career full of notes dating back to almost anything, 3x5 cards, a lot of that going on. The notes that he produced for this podcast were 17 pages. It's amazing. It's just, it's got highlights. Yeah, it's got highlights. It's got, it's so good. We could do a week-long podcast on this motor and the NSR alone.
What came about was that Honda had to deal with Wayne Rainey at a point, and Yamaha at this time were very strong in torque, whereas the Honda was being made to turn pretty high revs, like 12,000 or 12,500, and it had a high top speed, and the engineers were very nervous about. They felt that the crankshaft should be as light as possible because the crankshaft mass can reduce top speed. And the various riders, Freddie originally, and then others, found that the bike pushed the front. And they said, we think the engine should be forward. And the engineer said, oh, we can't do that because you put too much weight on the front and the steering gets heavy. And it turned out that what was going on was all these companies have a program of moving engineers around from one job to another, and they feel that this is desirable because it gives a good overview of what the company's activities are. But in this case, it brought people from production side to the race team where their prejudice against weight on the front wheel conflicted with the rider's need for the front wheel to stay on the ground rather than constantly popping up and being light in corners. When you're trying to accelerate off a corner and the front wheel goes light, you see riders come in after that with making that gesture showing that the front end has closed. They're having to steer in more and more, trying to increase the bite. Then it lets go and the bars turn in. So they managed to get the engineers to trust them. They moved the engine forward a couple of times. The Honda engineers were getting it, sort of. But big fly in the ointment, of course, was Wayne Rainey, and the solid torque of the Yamaha. They used to talk in those days of there being Honda lanes at faster racetracks, where I think Mr. Ito on the fuel injected variant of the NSR500 achieved 200 miles per hour. But of course, races are not won by top speed, they're won by acceleration off of corners. And it took time for the company and its decision-making apparatus to get the message from the riders, from the trackside people, as to what they really needed. And this is often a problem in any type of undertaking like this. For example, pilots versus aircraft engineers. The aircraft engineers aren't up there struggling with pitch instability. All they see is drawing lines on graph paper. So this process took a while, and Wayne was a powerful force, winning several championships. Lawson managed to win on Honda in 1989, and he wanted the chassis stiffer, and they kept on asking for this. Please, we would like. And eventually they said, how about this? They gave them a chassis that had essentially doubled chassis beams on the side. It was stiff enough. And there were several kinds of swing arms. There were the swing arms that consisted of a conventional swing arm with a bracing made of tubing welded onto the top or bottom. And then there was the solid type, which is what you see in MotoGP now. The whole thing is a sheet metal structure. You can't see through it from the sides. A lot of this stuff was being created for the first time out of the conditions of trying to deal with that tough guy, Wayne Rainey. And there came the unfortunate day when he was injured, and Mick Doohan wasn't doing so well, so there was an interregnum. That was the year 93 when Kevin Schwantz was champion on Suzuki. But the big news in terms of technology in that period was a Big Bang firing order, because Honda had started out with 90-degree firing order, so that every 90 degrees, one cylinder would fire. The power delivery to the rear wheel was thus very smooth. But that didn't impress the rear tire.
It sounds good intuitively, though.
It does.
Right? Doesn't it?
Because
Oh,
tires like smoothness. They like constant load. They don't want a lot of yanking and hammering. And so the engineers were just puzzled when the rider said, if we're coming off the corner with a Yamaha guy, the Yamaha guy can start throttling up before us. If we try to throttle up with them, we slide out. Oh, how can this be? And somehow a trial was made with an NSR500, which at the time was a V-twin, and they tried close firing order, and they found some benefit. So they built a 180-degree engine, and that was better. Now they had parity with the Yamaha guys. They could accelerate with them off of corners, but people were still scratching their heads over how does the rear tire know when the cylinders that are all putting out the same size bangs, when they're firing? So Honda did a bunch of really exhaustive testing, because this looked like the beginning of a solid seam of gold in this mine. So they just started digging like crazy. They tried all kinds of stuff. And what they found was a sweet spot at 67 or 68 degrees. 2 cylinders fire, then say 67 degrees later, the other 2 cylinders fire. So it goes kabang. And then there's a pause of 290 something degrees. This thing was phenomenal. It improved grip during acceleration off of corners that was so tremendous that the other manufacturers, nobody asked any questions. Nobody said anything about Yamaha way. Do it. And so they all began to sound like 500 motocross bikes. They were deep and grunty. And they began to break clutch baskets. They began to break gears. So everybody had to hurry and reinforce all those parts. But of course, what was happening was, we all know that if you've got a big crate to move across the shop, you got to have 4 or 5 guys to get the thing moving. And then a couple of them can step away once it's moving, because sliding friction is less than static friction.
Did that exact thing with my mill. I bought a mill. I got it off the lift and into my garage. 3 of us, I got this really thick, heavy duty neighbor to come over, football type.
Thick, heavy duty neighbor, yes.
And I'm like ready to help him push the mill across, and we go, and we get the thing moving, and he just takes off all by himself, just slides that. It's like it was a 54-inch index mill. Index was I think, Michigan manufacturer.
Yeah.
And it weighed 2,500 pounds. And that guy pushed, once we got it moving, he just put it right where it was supposed to be. It was magnificent.
Wonderful. Yeah.
Yeah.
So what they found was that in lower gears, the bike rolls forward about a full footprint during that 293 degrees of quiet time. And when no cylinder is firing. And during that time, the fresh footprint is laid down without the engine yanking on it. And that allows it to recover something like static friction. Whatever it is, the rubber bulging down into the profile, the texture of the surface, the roadway surface, or the formation of little molecular bonds. Whatever it is, the more time you give it, the stronger the static friction effect. So then you unleash those 4 cylinders over 68 degrees, and they give a god-awful yank on that well-planted footprint, and your bike is hurled forward in a satisfying manner.
Rinse and repeat.
Yes, just so. So that's an example of Honda's resources enabling them to say, I want you to find out about this. This looks promising. And they just put a bunch of engineers on it and assign some budget and go do it. And never mind the fact that at the moment, when the Japanese manufacturers are doing well to get a bike into the top 10, it's not working like that right now. But organizations, they're not easy to deal with.
At that time, the reputation, was always Honda technology, and they were always, at least externally, they certainly appeared to be investing more in exploring many, many ideas. As you said, Mr. Oguma, his refrigerator, correct?
Yes.
That one? Yeah. Where they would research something and you say, well, this could be useful in the future. And they just throw it in the fridge and pull it out, when the time came to make a meal with it. And it seemed to be that Honda was able or had had put more money into
R&D
doing
to
that.
burn.
Yeah.
Yeah. Well, and of course, they tried that gas tank under the engine thing. It didn't work out, but they tried it. And nobody else ever tried it again since then. So what this all came down to was, after they had made the breakthrough with the Big Bang, and another breakthrough that they had made was made in a very traditional way. When a new model comes to the racing department, it has been designed by engineers with degrees from Tokyo University. And basically what it is, it extends with a dotted line performance trends that were proved in the previous season. So we're going to make it. It was good. Now we're going to make it better. And they wheel that thing into this shop where there are these two guys. One of them was known as Lobsterman, and I tried to find out who he was when I was in HRC in 2020, but that was a head scratcher. Oh, we don't know. These two men had the responsibility for getting the horsepower out of the new design. And they had a modular exhaust pipe system by which they could quickly rough out how long the header should be, how long the horn, how long the center section, and so forth, so that then when they brought in the welders and the sheet metal rollers, they could get the fine details right. The center section may need to be 3 millimeters longer or shorter than that in order to really make the mountain peaks coincide, so you get a tremendously strong effect. But those men discovered something that Yamaha was working on very tentatively in 1978, which was to turn the second set of transfers, the so-called B transfers, the A's are the ones that are on either side of the exhaust port, to swing those things what seemed like backwards in terms of intuition, point them toward the exhaust port. And what that seems to have done is to allow the 5 streams entering the cylinder to crash one another into a lower energy state, so that instead of a single jet of fresh mixture going up the non-exhaust cylinder wall across the cylinder head and down to the exhaust port in the twinkling of an eye, resulting in a power band that you can't even get through sideways, it produced a cylinder filling generosity. It was quite wonderful. I made a conversion for TZ750 employing this idea. I might modestly say a couple of years before Honda did it, but it works so well. And those men must have felt pretty jolly when they came up with this, because it was worth about between 2 and 4 horsepower per cylinder. And it got them from wherever they were to something more like 160 horsepower for the whole engine. And these men were experienced, but they also knew that trial and error requires the ability, like a good salesman. The salesman goes to 9 doors and they all slam in his face. He's got to go to the 10th door with the same cheerful attitude and sell the daylights out of that Encyclopedia Britannica. So those men were busy this whole time. Years this took. And when they finally had their motorcycle emerged, and Mick Doohan had a period that was pretty much clear of the injuries that he was vulnerable to, he put together 5 years of solid success. So solid that someone in some publication said, why doesn't he slow down and make a race of it? So what had happened then was that they had a reliable engine. They knew how to make the kind of power that Doohan could accept. And Doohan, for his part, said, I am here only to win races, not to test engineers' ideas. He was known to say, when he was told, okay, we've got a different front end on this bike for first practice, take it off. I'm not riding it with that thing on there, because I'll waste the whole practice trying to figure out what that different front end is telling me. And if it doesn't tell me accurately, I'm going to hurt myself. Then where will we be? So he constantly tried to make the motorcycle more rideable, and quite often the changes required for that reduced the top speed. So he would have a dominant lap time and an indifferent top speed, repeating the great lesson in racing, which is the top speed. We pay attention to it because it's a big, impressive number. But you only get to use it on that one or possibly two straightaways. Whereas there are 12 or 14 or however many corners off of which you must accelerate. And if you have smooth power, controllable power, and power that's wide enough that you don't have to shift gear in the middle of a critical operation, you're going to leave the others behind. Now, you mentioned ATAC. ATAC was a resonance chamber up near the exhaust port with a valve. And it could turn the exhaust pipe from this frequency to this frequency and add about 500 RPM below the normal torque threshold. So that was useful because it meant less shifting, less upset for the tire, more like what Doohan wanted. They came up with another wonderful, well, no, wait a minute. The ATAC was used for several years, and then they finally switched to Yamaha way, which was a variable height exhaust port that opened at different heights, depending on how the gates were raised and lowered. And if you've seen Kawasaki motocrossers, you'll know that they had a divided exhaust port, and the gates were quite complicated, and Honda had to deal with problems associated with extra heat affecting the cylinder, probably distorting it, causing leakage. But that's just engineering, more testing. And the variable height exhaust port broadened the power band even more. And that was used right to the end. At one point, maybe it was 96, the engineers came with water injection. Well, the resonance of the organ pipe, namely the exhaust pipes on the engine, one for each cylinder, depends on the velocity of sound in the pipe. So if the gas is very hot, the pipe resonates at a higher frequency. But if you can cool the gas, it will resonate at a lower frequency. So they thought, let's spray water into the header pipes and see what that does. Well, it allowed the engine to pull from 6,000, which otherwise is just like, are you kidding? Because what happens with these 500 cc's doesn't sound big, but it was big in those days. When a big two-stroke hits its torque threshold, torque typically doubles, which means wham, on the ground if you're working the tire hard at that point. So
yeah, it's hard to communicate what a two-stroke as a non-ATAC, variable exhaust port, just a straight up, we need to make power here.
Yeah.
The way that it would come on, like in an RD 350, TZ 350, 250, where it was just it just shoots up. It's it's that Schwantz roll, right?
Yeah, you're having to turn it back
Revs are
while it
rising,
accelerates.
revs are rising, and we're rolling as it's coming up. We're closing the throttle to try and keep the output in a linear manner. It's just, it's insane. So that having that flexibility as a rider for somebody of, Doohan's magnitudinal talent is it's what a weapon it would become to have that flexibility.
So eventually he was injured again, and he decided, okay, that's enough racing. And like Kenny said years before, he said, racing, typically a good rider has 10 years at the top. He said, it's like something is used up, and when it's gone, there's no point in continuing. So Doohan bowed out. Alex Crivier took one more championship on the NSR. Then he ran into health problems. The year that he won, this brash kid, Valentino Rossi, had his learning year on the bike. And he said later, Alex wanted the powered up version of the engine. And he said, you can do one fast lap on this engine, but 24 laps are another story. So Crivier was out of the system, and Valentino Rossi won his first 500cc World Championship on the NSR. So, and of course, Kenny Jr. was in there somewhere. The NSR went to the museum then, because it was like the development of aviation during wartime. The development has to go on while the combat is at its most intense. You have to provide adequate reliability, even though you don't know whether the power increase that you're hoping to fly to Europe in 3 weeks is going to be equally reliable. And it's probably a good idea if we all work through the night on this one. And so it was really a classic story. Trying A, trying B. And as they got a better grasp of what was required, the motorcycle began to be this beautiful work of art. Those close-ups, side views with the fairing off of NSR 500s are framing quality. I wish I had one on the wall right here, because they had an engineer whose whole duty was to make the individual parts look as though they had been produced by the immortal gods, so that when the members of the other teams looked upon them, their hearts would sink, and they would think, why don't we just go home? And I hope that particular engineer is enjoying a pleasant retirement, because he did things like the following. When you pull the clutch or the brake lever, the end normally bears on the exposed end of the hydraulic piston that produces the pressure in the line. Oh, we can't have that. We must have a roller on the end of the brake lever. A roller? Yes, well, needle bearing. Let's put a needle bearing in there. But Grant will get in. No, we'll have a seal, one on each side. So all these part numbers. What a smooth pull.
I think it was Peter Egan said that about a Honda. I think it was a VFR 750 he was writing about, and he said that Honda Hondas feel like they have little bearings inside of every pivot, and in that case, they did.
Yeah,
So,
yeah. So they eventually produced a motorcycle which remained essentially static during the 90s. In the early 90s, the FIM said, now we're going to low lead fuel as a sort of the beginning of the lead removal process. Now, tetraethyl lead is dreadfully poisonous, but it is also a potent anti-knock catalyst. What's happening to produce knock is that a chemical fragment known as the free radical, OH minus, oxygen, hydrogen with a negative charge, is produced by the pre-flame reactions when you get unburned mixture really hot, up over 900 degrees. And when the population of these OH minus guys are in there, like troublemakers in a bar, guys that are getting restless, then you need the anti-knock catalyst, tetraethyl lead, which basically suppresses, it turns the production of OH minus down so that instead of the population rapidly increasing and resulting in knock, hold off a minute, not just now. And there are a lot of cases like this in which something that's tremendously effective, Hooker Chemical was well respected for some of their products before they became famous or infamous in the case of the, what was the name of that dreadful Love Canal, the Love Canal disaster.
yeah.
But they were following their industry standard. So tetraethyl lead had to be removed because exhaust catalysts were coming in, and lead liked to occupy all the sites and turn the catalyst off so that it couldn't do its job of completing the combustion of unburned fuel. Anyway, then at the end of the 90s, no lead fuel came in. So they were having to deal with these changes at the same time as they were providing Mick Doohan with a nearly constant motorcycle whose communication with him was not being interfered with by novelties from the engineering department. And this is a wonderful example of what can happen when there is such good cooperation between an outstanding rider and the people who are supporting him in the field. So I was surprised when I went to the Motegi Museum in 2020. I'd never been there before. And there was a late model NSR over by a window, and I went to look and reading the provided material, and I'm looking at the engine. Oh, crankcases are water cooled. Nice one. Because here comes the mixture. Fuel is spraying in the carburetors, 4 of them. And the evaporation of the fuel is cooling the intake flow, but now it's flowing into a hot crankcase. Air temperature up. Now it's going up through the transfers and into the even hotter cylinder. Now here comes a piston that's pretty hot, compressing it up against a cylinder head that's also hot. So when they got rid of the lead, they had to do things like make the cylinder cap out of high conductivity copper, and they had to, Yamaha did anyway, they increased the thickness of the pistons to nearly 1/2 an inch to provide a good heat pathway from the center of the piston dome, which is the hottest place, outward to the cooler cylinder wall. And cooler it was because all these two strokes were running hot bathwater coolant temperature, like 135 Fahrenheit. You wouldn't want to be in that water, but it's a far cry from the 190 that we expect from production stuff. The whole idea there was to keep the crankcases as cool as possible and the cylinder, especially around the exhaust port, so that the fresh charge coming in did not get too far in the direction of detonation as its temperature rose and the production of OH minus, those naughty boys, increased.
And nothing works better than tetraethyl lead, right? That's kind of our number one anti-knock compound.
Well, they were very thorough. This was in the early 20s, and I think Delco employed an engineer whose name will come to me presently, and they said, sort this out. And he had dozens of test engines running constantly, and they were testing one compound after another. And they found that there were some iron compounds that were promising, and they found that there were manganese compounds, but the one that really did the job was lead tetraethyl, which unfortunately is hideously poisonous.
I discovered that when a friend of mine worked at a chemical company, and I was struggling with British cars, getting good octane and getting anti-knock and being able to get the performance out of them. And he worked for a chemical company. I said, "Well, how can I just get some to add to my own fuel?" And he's like, "Oh yeah, I'll look into that." And he's like, "Oh my God, no! It's the drums are on scales. It's heavily regulated, and it's fantastically toxic. Like you don't want it. You don't even want it.
No.
We all have dreams.
A similar material used to be used. What was it? The mercury compound, dimethyl mercury, was used as a standard for the maximum toxicity, and they had to stop using it because a drop on your skin kills you. It just kills you. And there's no point in, it's like, well, geez, Dad, been great knowing you, and I can't say I'll see you later. So lead is gone, but the fuel that they brought immediately when the lead ban took effect they called it chemistry set fuel. It had 5 elements in it, not elements, 5 compounds. There was the 4 good octane structures. Octane just means 8 carbons. It had tryptane. It had toluene. It had MTBE. And so that the engine would cold start, it had isopentane. Isopentane has an anti-knock rating of about 91, so it's no mystery cure for anything. It's just that it's very volatile enough to make your engine cold start. So those 5 things were their initial recipe for making lead-free fuel. And after that, the FIM kept dicking with it and turned it into something that cost like a cocktail in New York City. So that chapter came to an end in 2001, and the following year, MotoGP began. For a short time, if you were in the MotoGP paddock, you could go down to the end for a smoke because all the 125s and 250s, which were still 2-strokes, were down there. They were warming up. You could
get a whiff of the past.
Yes. And change happens.
Yeah.
There are ways that 2-strokes can be made to pass emissions laws, but it is not economically advisable because what all the motorcycle manufacturers did, rather than heroically saying 2-strokes forever, is that they said, let the automakers develop the emissions control technology, and then we'll go down to the Napa store and get it. And ask them for a discount, will you? And that's the way it's been. The automakers developed all of that stuff, the engine crawling with black hoses, all of which were cracking and leaking. 1977, stutter and stall. And now we have emerged onto the sunny uplands of digital fuel injection. And cars just start and run, and so do motorbikes. And they perform well because it turned out that time that all those elements, digital fuel injection, fuel worse than the Army Air Corps was burning in 1935, and computing technology, it all went together gloriously and produced the well-running bikes and cars and light trucks of the present moment.
Well, it's crazy because you can go pull one of these test bikes out of here, like a new MT-07 or an MT-09 Yamaha, and get it out in the parking lot, thumb the starter button, runs perfectly. It's ice cold, or as cold as ambient, and then you could do a wheelie. You could throw the clutch and just wheelie out of the parking lot with a cold engine, and
Yeah.
it won't even tell you. It's crazy.
It knows how to do it.
It's so good.
Yeah.
It's just remarkable. One thing I wanted, we're getting close to time, and I hope this isn't too big of a question to tackle, but it seemed like everyone ended up with the 54 by 54.5 as the cylinder that they just used. They used it in 125, and then they just put two of them together for 250 and then 500s.
Yes, they did. And Yamaha started out with two bore and stroke arrangements. One was 54 by 54, and the other one was 56 by 50. And of course, when it became important to be 249 rather than 248 point something, they added fractions to the stroke. But the basic fact is we're all conditioned to think that larger bore and shorter stroke is higher performance. That is four-stroke thinking, and it is appropriate there because the short stroke allows for a given RPM a reduction of piston acceleration, which helps reliability or allows you to run up to higher RPM for higher performance. And the larger bore provides room for the big valves that can fill and empty the cylinder at the higher speed, that is the higher RPM that's made possible by the shorter stroke. So yes, for four-stroke, big bore, short stroke is the direction of higher performance. But with a two-stroke, the ports are in the cylinder wall. And it turns out that by making the stroke longer, you make the ports bigger. And it's not a night and day effect, but they all tried 56 by 50 and ended up at the end of the two-stroke era at 54 by 54.5. Honda did try an engine that was like 50.5 by 60 in looking to take advantage of the larger port areas. And they did some testing with it, and they didn't go forward with that idea, but they did the due diligence. And I think one of the engines that was limited by too big a bore and too short a stroke was Yamaha's TZ350 and the RD350 on the production side, because it was 64 millimeter bore by 54 millimeter stroke. And they thought they were doing good in Grand Prix racing to get 80 horsepower from that thing. And by 1994, 10 years after the 350 class ended, Honda, sometime during that year, I think, achieved 100 horsepower from a 250. So, of course, there was a lot of technology which, had it been applied to the 350 twin, such as taking the two cylinder bores and swinging them apart so that those cup handle transfer ports, transfer ducts, could be used instead of the ones that are crammed tightly between the cylinders, go up, and then have to make a sudden right angle turn to enter the cylinder. That was a built-in 2/3 throttle, which is why 80 horsepower was about it for that engine. But when they had the choice, two-stroke people went for equal bore and stroke as the best compromise between piston stress and port area.
Excellent.
At least that's as far as our thinking got by that time.
Yep. And then we moved away to 990s.
Indeed.
That's something else entirely. 990s, 800s. Slow these things down. Oops.
Yes. That often happens, though. Formulas changed. They state an ambition for the formula. It turns out to be something entirely different because everything is changing all the time. For example, there is a piston material that's twice as strong as the current 2618, all those forging alloys that are derived from Y alloy from 1916. It's aluminum reinforced with tiny fibers, tiny ceramic pieces, and it's expensive to make at present. But you can be sure that if it was essential for somebody's war effort, they'd find a way to bring the price down. So no telling what four-strokes could do if that piston material became widely available at a reasonable price. This is the kind of thing that happens in engineering, is just when you think things, oh, I've got a grip on this, something changes and it's all different. Got to think again.
All right. Well, thank you for listening, folks. This episode, as usual, is brought to you by Octane Lending, our parent company. There's a link in the description to the Octane Prequal Flex. You can pre-qualify, see what your spending ability would be getting a loan from Octane. Go check out the tool. Click on the link. Even a click on the link is helpful. Just check it out. We thank Octane Lending for making this possible because we wouldn't be here without them. We'll catch you next time. Thank you for listening.
Yes, indeed.